Last year, the mining industry extracted over 2.5 billion tons of iron ore from the earth. Most of that ore was used to make steel. And that steel, about 500 pounds for every person on the planet, became the cars and buildings and bridges that form the landscape of modern life. Welcome to Ask MIT Climate. I'm Madison Goldberg. And this morning, I rode a 60-ton steel train car to work without once thinking about the material that made that trip possible. Today's guest, however, thinks about steel a lot.
I'm Antoine Allanore. I'm a professor of metallurgy in the MIT Department of Material Science and Engineering. Steel is a product that has a unique mechanical performance, corrosion performance. It can sustain high temperature, low temperature, magnetic field, electric field. It's also very easy to join. I mean, if you look at the building construction in any modern city, the rate at which steel can be erected and welded together is so fast. I mean, it has basically this versatility that makes it really an unreplaceable material.
It's not an exaggeration to say that without steel, we couldn't live the way we do. To make a truck or a skyscraper, you need a material that's strong and durable like granite, but also malleable like plastic. We also need a lot of it. The list of materials that fit the bill? Well, there's approximately one. Today, we're going to talk about what all this steel means for the climate. And that starts with the basic chemistry of steelmaking.
Earth doesn't give you steel. Earth gives you iron.
And the iron ore that comes out of the ground is not pure iron. Instead, atoms of oxygen are bound to the iron. So steelmaking is, first and foremost, the chemical art of getting that oxygen out. To do that, you need to combine the ore with something that's good at grabbing oxygen. In most modern steel mills, that ingredient is coal. Crushed up coal and iron ore are combined in a gigantic blast furnace, which gets its name because a hot blast of air is blown inside to get the crucial reaction started. At these high temperatures, the carbon from the coal starts to yank the oxygen loose, and what comes out of the furnace is a molten stream of nearly pure iron. Now, at this point, we don't have steel yet. There are more refining steps to get to the precise chemical mix that gives steel its incredible properties. Mostly iron with a tiny percentage of carbon and other trace elements. But since we're thinking about the climate, the blast furnace is the step we're most interested in. And you might be able to guess where this is going. As the carbon from the coal grabs oxygen, you end up with carbon dioxide, or CO2, the most important greenhouse gas driving climate change. The global steel industry creates about 2 tons of CO2 for every 1 ton of steel. And there are 2 points to make about that number. First, relatively speaking, it's actually really low.
In terms of energy consumption per ton of metal, it's one of the lowest ones. There is much more energy needed to make aluminum, for example, which is the second one you could think to substitute iron for structural application. But the answer is no, you need a lot of energy to make aluminum metal, much less for iron.
But here's the second point. At the scale the world produces steel, that CO2 adds up fast.
We're talking about billions of tons. So you multiply billions of tons by 2, and you get like 7% of the greenhouse gas emissions attributed to iron and steel production.
The steel industry creates more climate-warming CO2 than any country except China, the United States, and India. And Professor Allanore says steel production isn't likely to slow down in the near future.
The reason why China has become this giant in iron and steel in the world is because they needed to build more infrastructure, more town, more high-speed rail, and so on and so forth. And I don't really see how it's going to be different for other regions, Nigeria, India. Those regions, they're going to demand the same quality of transportation, safety, shelter. And there's no other material than iron to give that to people.
So, is there a way to produce the steel of the future without further heating the planet? Well, Professor Allannore's lab is experimenting with a technique that aims to do that.
I'm Matthew Michalek. I'm a third-year Ph.D. student within the materials science department. I study metallurgy, and what I do here in the lab is a heady topic called iron oxide sulfidation, but what that really means is I turn red rocks into gray rocks.
When we're working with the iron as a sulfide, it presents very different opportunities than thinking about it only as an oxide. And I'm Katie Daehn. I'm a research scientist working with Professor Allanore. I've done work with experimental metallurgy, figuring out can we extract metal in a more sustainable way.
When we visited the lab, the team was wrapping up one of those experiments to turn a red rock into a gray rock. That experiment took place in a small furnace hooked up to a bunch of wires and tubes. It wouldn't look out of place in an industrial kitchen, but before our visit, it had reached temperatures hot enough to melt bronze.
So we ran an experiment on Friday on some oxide, and what I do is essentially there's that little pole down there, and that's flowing inert gas, nitrogen, through the setup, and I'm using it to slowly raise a crucible of sulfur up into a hot zone, and then as the temperature goes up, the sulfur begins to evaporate, and that creates a reaction, and I'm going to open the furnace, and I can show you around, and then maybe we could look at what we see at the end.
The end product was a charcoal gray lump about the size and shape of a large pencil eraser. At the beginning of the experiment, the lump had contained oxygen, like the iron ore used in steelmaking. But now, instead of oxygen, it contained sulfur. The team has been studying this transformation, going from iron mixed with oxygen to iron mixed with sulfur, to learn more about the precise chemical reactions involved.
When these reactions occur, the primary gaseous product is sulfur dioxide, and we can measure the concentration over time of that, and then if you find out that takes 5 minutes or 10 minutes, that should tell you how long that chemical reaction takes at the atomic scale, right?
That's important about the scalability question, right? The truth is that if you don't have these fundamental steps that Matthew is talking about, you can't really imagine designing a, 200-meter long furnace at, $500 million. Like, that's not going to work. Like, somebody's going to want to know, okay, how fast is it going to happen?
The idea here is to change the chemical nature of steelmaking. If you're not combining carbon and oxygen anymore, then you don't get climate-warming CO2. And it also takes less energy to pull sulfur away from iron than it does to pull oxygen away, which would help this process compete with traditional steel mills.
So it's a way to then completely divorce from carbon emissions. And we can do this all at high temperature. So we can make steel at what we think are rates competitive with a blast furnace. We've been working on this for some years now, but to the kind of wider world, it still is a very new technique, something a bit out of the box. And so we're just trying to see, what kind of legs it has, if it can continue scaling up.
So this is still really speculative, and it's attempting to replace chemical reactions that steelmakers have relied on for literally thousands of years. So why is Professor Allannore's team exploring this new method? After all, there are other ways to make cleaner steel. For instance, you could replace coal with a clean fuel like hydrogen. That way, when you pry out the oxygen, you just end up with harmless water vapor.
Historically, it's very fascinating. You can read papers from 1950s, 1960s, and there are like 20 different reactor technology to use 5 different types of fuels. So they've all been done at one point at one scale. And they all work because steel is not very difficult to make.
There's also a process called electrolysis. This doesn't use fuel at all. Instead, electricity separates iron ore into its chemical parts.
If I put iron oxide between 2 electrodes with enough voltage, suddenly oxide wants to go one way, iron wants to become iron metal. If you look at aluminum, so aluminum is made 100% by electrolysis, where the feedstock is alumina, aluminum oxide, so it's exactly the same.
This is what the lab here at MIT hopes to do with their sulfur-based method. Professor Allanore is also the co-founder of a company working on electrolysis with regular iron ore, and he's not giving up on it, but he notes that the technology hasn't yet produced a commercial steel mill.
As a researcher and an engineer, it's interesting to ask ourselves why. What's so difficult? Like every metal on the periodic table, there is an industrial electrolytic process to make it, but not for iron.
So far, all these concepts for clean steel have run into the same problem. They're competing with one of the most efficient industries on Earth. A traditional blast furnace can produce a more or less never-ending stream of liquid iron.
There is almost no energy loss in the blast furnace. All of the energy that has been spent is going to be used where it's needed. That is to say, in the chemical reaction to make sure that the temperature stays the same and the liquid metal can be formed. What I'm trying to say is like the furnace operates all the time. All the time you're feeding iron ore and all the time you're tapping liquid metal. It's a bit different than the oven with a pie where you have to open the furnace, you have to take the pie out, and if you want to do another pie, you put another pie in. Well, everything I just said, it's basically time where you're not making pie.
So the iron keeps flowing without energy wasted heating the furnace back up or cooling it down. The iron can immediately be refined into steel. Plus, it already has some carbon in it, which the end product will need. So there are far cleaner methods of making iron. But the iron you get from these methods takes more energy and effort to refine. And Professor Allanore says at the scale big customers are used to, these inefficiencies add up.
I'm not talking about 1 ton. I'm talking about, 10,000 tons of this product is going to be needed by that industry. And I want to be the one providing it to you. And yes, price will be important, but reliability, quality, availability is also a criteria that is very important for somebody to accept to buy from you. And that's the landscape into which new technology will be deployed.
That's not to say researchers and companies aren't trying. The company Professor Allanore helped found is still plugging away at electrolysis. Sweden is home to a hydrogen steel company. And people are going after other outside-the-box ideas to reimagine how the world can build the cars and cities and bridges of the next century.
And hopefully some of it can be made with these new technology that are cleaner, but ultimately what's going to matter is it available, is it of good enough quality, and more importantly, can we afford it?
And Professor Allanore says that question is, forgive me, a very effective fuel.
There's nothing better than constraint on price to make you creative about how can I make this material to the price that the car industry is willing to buy or the construction company are willing to buy.
Ask MIT Climate is the climate change podcast of the Massachusetts Institute of Technology. Aaron Krol is our executive producer and the writer for today's episode. David Lishansky is our sound editor and producer. Michelle Harris fact-checks our episodes, and the music is by Blue Dot Sessions. And I'm your host and associate producer, Madison Goldberg. A big thank you to Professor Antoine Allanore, Dr. Katie Daehn, and Matthew Michalek for speaking with us and showing us around their very cool lab. You can find more episodes of the show at climate.mit.edu. We're also on TikTok, Instagram, and YouTube at Ask MIT Climate. And if there's another climate topic you'd like us to take a hard look at, send us an email at askmitclimate@mit.edu.